What we're doing is we are climbing back into 5.3. We finished up the identities. We skipped over the solving trig equations. So what I wanted to do today is really go back to the fundamentals and say, can you just solve when a trig function of some angle is equal to a ratio? Now remember, sine and cosine only have ratios as big as 1 and as low as what? Negative 1. Because that's the values of the sine and cosine values on the unit circle. Now, we did actually do some of this back in chapter 4. And if I asked you to solve the cosine of theta equals 1/2, cosine's a function. To get rid of a function, you generally use another function. Which function would be able to be used to get rid of a cosine? Tangent would not be a good option. Not secant. How about the inverse cosine? The inverse cosine would be enough to cancel cosines. Now the reason I can't use secant, which is 1 over cosine, is because you can't cancel the actual function away, leaving you with the values inside. You know, theta doesn't get to stay then. It would change it to 1 instead of theta. But what I do to the one side, I have to do to the other side. And so I have the cosine inverse of cosine theta is equal to the cosine inverse of 1/2. So these two definitely cancel each other out. Theta is equal to the cosine inverse of 1/2. We've done this before. As in, we've solved this. We said, hey, when I'm solving this, cosine inverse exists in only 2 quadrants. Which 2 quadrants are they? 1 and 2. It only is in 1 and 2. But I'm talking about a positive ratio. So which quadrant?
1.
Just 1. And if I do this, I am forming a triangle, and there's theta. This is 1/2 over 1. Or, if you want, it'd be 1 over 2. And we could technically use our reference triangles or Pythagorean's theorem to do all of this. Or I could just go to my unit circle. Which angle, when I take the cosine of it, gives me 1/2? What's the angle? 60 degrees. Or, if I felt like it, it's pi over 3, isn't it? Pi over 3, 60 degrees, one's in radians, one's in degrees. Now, here's the thing. That's not wrong. It's right. But what if I told you it's not complete? It's not all solutions. Because if I said solve an equation, aren't you supposed to be looking for all solutions? You can't just randomly choose a particular value of x or theta and say, this is the answer, so therefore I'm done. You should always find all of them. So this method of taking the arc cosine or or inverse cosine doesn't necessarily give us the full picture. What we need to realize is that cosine itself is positive in how many quadrants? It's actually positive in 2 quadrants. What's the other quadrant?
4.
It's down here. Is there another angle down there that has a cosine value of 1/2?
300.
It's this one, which is 300, isn't it? But notice that I put theta in there anyways. Why would I put theta in here? What would this angle actually be? It could be a negative 60 if I start from the top and go downward, right? But it's technically still 60 degrees. 60 in this bottom triangle, which is still the same as this 60, is considered a what kind of angle? Not coterminal. Reference angle. Right. Reference angles have the same sine, cosine, and tangent values. You just need to affix the right label as in sine, right? If it's in certain quadrants, it's positive or negative. All students take calculus. All schools torture children, whatever you guys want to use. But, so that means, if I was looking from 0 is less than theta, which is less than 360, so 0 is greater than, or less than or equal to theta, which is less than 360, theta would equal 60 degrees, theta would equal 300 degrees. There are two prospective answers on 0 to 360 that if I took the cosine, I get a half. Positive 1/2. And if by choice or chance I was looking for angles between 0 and 2 pi, I would say theta is equal to pi over 3, because 60 goes into 180 how many times? And 5 pi over 3. I'm going to slowly ramp these up to be a little bit more difficult, as in, not difficult as in the, I'm trying to think of the right word, difficulty. The process is just different, but not necessarily the concept. So it's just more steps. Because there's more steps, I'm going to call it more difficult. To do this, to solve this equation, I need to get what by itself? I need to get the sine theta by itself. So the hardest part about this, or not the hardest part, the added layers to this, it's almost like one of the solving a two-step problem, two-step equation. Before, instead of solving it as a two-step equation, you have to solve for sine of theta after, or theta after you get sine by itself. So the first step here would be what? Subtract square root of 3. So 2 sine theta is equal to negative square root of 3. Divide both sides by 2. And so you get negative square root of 3 over 2. I'm going to change things up. I think most of us would agree that to get rid of sine, I have to take the arc sine or the inverse sine. I'm going to get away from that idea. Instead, I'm going to go with that second option that I kind of talked about before. And I say, wait a minute. Sine of some angle, degrees or radians, it doesn't matter, is going to have a value that's negative. Ignore what it is right now. It's negative. You know this angle has to be located where? Third or
well, it's negative, so
fourth. So we know how many answers?
we know
2 answers. And both of these answers are based off of the square root of 3 over 2. Now, I could stop right now, look at my unit circle, and say, what is that angle? It's on my unit circle. 240. And the other one, all the way across? 300 degrees. They're on my unit circle. I got them. Yeah. Or it's 4 pi over 3 and 5 pi over 3, right? If I'm in radians. Now, what if I didn't have my unit circle on me? What if I only had the reference triangles? Or I only knew enough information because I remember the first quadrant. Ignoring the negative, what angle, when I take the sine of it, has a square root of 3 over 2 in it? There's 60s, which means that each of these angles that we just found have reference angles of 60 or pi over 3. So you know that if I took 180 plus 60, where am I at? 240. If I took 360 and I subtracted out the 60, where am I at? 300. So, keeping with what we were doing earlier, if I stated I wanted to know theta between 0 and 360, well then theta is equal to 240 degrees, and theta is equal to 300 degrees. You're done. Yeah? Now that seems pretty easy. I got another layer of complicity here, but let's add another layer before we get to that one. If I asked you to draw a sine or a cosine curve, would it just look like this? Done? Is that a sine curve or a cosine curve? Could be, right? I mean, it's a pretty crude drawing. But does it really ever stop? No, it should actually just flow until it goes off your paper, right? In both directions. What it means is that it hits the same value how many times? An infinite amount of times. Okay? So that means that the sine curve is going to hit a half, a half, a half, a half, a half, right? When do these things happen, though? When does sine equal 1/2? Or even, let's go back to our problem here. Let's go back to, we'll go with this one because we only have degrees on here. 240. If I took the sine of 240, I would equal negative square root of 3 over 2. Right? We just found it. But couldn't I start here and add 360 degrees, and wouldn't I be right there again? I could add 360 again. Wouldn't I be right there? Wait a minute, could I subtract 360 and be right there? Do it again, and again, and again. Someone's already said it today. What are those kind of angles to each other? Coterminal angles. And coterminal angles always have the same value, trig value. Doesn't matter if you're talking about sine, cosine, tangent, or of any of the little three. That's the beauty. But here's the complexity. If I go back up to this thing that's saying I only want answers between 0 and 360, well then there's only two answers on that unit circle. Only two of them are negative square root of 3 over 2. But if I go up to this answer and I go, gone. I just wiped it out. I'm not looking for you to tell me the solutions between 0 and 360. I'm asking you to tell me the solutions all the time, or all solutions. That's like solving a quadratic and only telling me the positive ones. Or telling me ones between 0 and 10. Where's the solutions? Even though there could be more. But now, I'm not doing that. I want all solutions. Here's the cool thing. We've already established what they are. It's 240 plus what? 360. Wait, what is that? What's 240 plus 360? 700? 600? 600, sorry. And then at 360 again, 960, right? Wait, I could subtract 360 as well, shouldn't I? Negative 120? And then I could subtract another 360, right? Just keep doing that. Just keep making a list. That sounds fun, doesn't it? Because I should be able to do the same thing with 300 now. But is this an exhaustive list of all solutions? No. It's only what? 1, 2, 3, 4 solutions. But there's supposed to be an infinite many. 4 is not enough.
Yeah.
1's not enough because I want all solutions. There's more than one solution. It's not.
There's an infinite amount
There's an infinite amount.
in both directions.
But what's the difference between every single one of them? 360. So, could I go back to here, get rid of all of that stuff, and say, wait a minute.
Just add the pluses.
Yeah, can I just add 360?
Then you get
But that, again, by doing that, just finds one solution, right?
n. But you
So if I don't, what if I want to add multiples of something, I need to introduce a variable. They introduced that k. Some of us might remember that. 360k plus 360k. K, guys, is a constant. It's an integer. It can be 0. Because if k is 0, what's 240 plus 0?
240.
It's 240. That's one of my solutions. If k is 1, it's 240 plus 360, which is 600. If k was 2, it's 240 plus 720. 960? That's another one. If k was equal to negative 1, I mean I subtract 360 from it, get negative 120. Are you seeing how adding that 360k now just lets me go around the circle over and over and over and over and over again? I could let k equal 1,000. It will be an answer. Okay? Now, going back to this one. We already talked about how to do that with this stuff, because that's the same, plus 360k, right? But what happens if I go here, 2 radians, gone. Find me all the solutions now. Solve this using radians. Plus 2 pi. Yeah, because we're not going 360, we are going 2 pi. Now, the book may use something different. Different books do different things. I personally put k after 2. So 2k pi. Plus 2k pi. And that's how you find all solutions. Because again, if I add 360 or if I add 2 pi, it doesn't matter. One's in radians, one's in degrees. And to kick it up one more notch for today, I'm going to add a square into there. And if the function's squared, to get the function by itself, you're probably going to have to take the square root.
So whenever you see a square.
Eventually, get the square by itself, the sign squared by itself, and then take the square root. Tomorrow, we're going to factor. We're also going to change our value of x inside to say something like 2 theta or 3x, which means we're going to have to go around the circle a couple times. Okay, so solve it. What do we do? Subtract 1. I think that'd be a smart move. Equals 3. What else? Divide by 4.
Wait, do you divide everything by 4? Or just the 4?
Well, you're dividing this whole side by 4. Equals 3/4, yeah? And take the square root. Now, don't forget, when you're solving for a variable and you take the square root, you need to have plus or minus. If I asked you guys the square root of 25, it's 5. But if it's x squared equals 25, there are 2 answers, plus or minus 5. Now, when I do this, I get sine of x equals plus or minus square root of 3 over 2.
So plus or minus, so it can be.
A plus or minus, so it can be both.
Can it be plus or minus x too?
No, plus or minus x. Plus or minus, sine of x is equal to. Which means, sine of x is equal to the square root of 3 over 2. Bless you. And sine of x could equal the negative square root of 3 over 2. How many solutions are there? There are 4. There are two positive sign values in the top two quadrants, and then there are two negative sign values in the bottom two. Now, here's a really cool thing, guys. Every single one of these angles has the same reference, right? The same reference of x. X is the angle, so x is the reference. You just need to ask yourself, when does sine have a square root of 3 over 2 answer? What angle? 60. So each one of these is at 60, right? Because the reference angle is 60. Unit circle or your reference triangles. Here's the cool thing. How do I get to 60? X is 60. How do I get to the next one? It's 120. How do I get to this one? 240. How do I get to this one? Now, since I'm asking you to solve this, each one of these has to have plus 360k. And you just solved it. It's all right.
What's the K? Was I going?
Now, here's an interesting thing. This is right. All of this work would be needed as support to find those 4 answers. That gets you 100% of the problem correctly. What if you wanted to go from 100% to 100% plus? How can I take this problem to the next level? Instead of writing this as 4 answers, what if I said you could write this as 2 answers only? Look at your graph above. There is a connection here between these 2 answers. Between these 2 answers, what is it? They're opposite, better. What's the difference between those? If I started at 60 and went to that 240, what's the difference? It's 180 or pi. If I started at 120 and wanted to go to 300, it's 180 or pi if you're in radians, right? So watch this. This is the cool thing. X could equal 60 degrees plus 180k. X could equal, not 240, but 120 plus 180k. Not every time, because our other problems, this doesn't work. But take a look what happens. If I start here at 60 and I add 180, I'm at what? 240, am I? And if I add another 180, I'm at 420. 420 is really just 60 degrees. Add another 180, I'm back over here. Wait a minute, I can go backwards. What's 60 minus 180? That is 240. Same position. So it doesn't matter if I go forwards or backwards, only by steps of 180 instead of 360. This only works for angles that are directly opposite each other. They differ by 180. Heck, there are times, guys, where you could take 4 answers and write them as 1. Don't spend all your time trying to find these things, but if you can naturally see it, go for it. So again, tomorrow we're going to go into factoring. You're going to find that if you divide, you'll lose answers, but if you factor, you keep them. And then we'll start to talk about maybe even going into some identities and changing things to solve them. Your homework, which you should have time in class, 5.3, day 1, page 331, 1 through 4. Have a great day. Sign up for the Pancake Run Walk.